Manish Gupta, and in this video, I'm going to talk about GalaXC, which is graph neural networks with label-wise attention for extreme classification. Okay. So GalaXC is a deep XML algorithm. It is a deep learning based extreme classification algorithm. It also makes use of graph label correlation graph in some ways, just like Eclair, but it is actually a much simpler algorithm compared to Eclair. Okay. In fact, the entire training of GalaXC can be understood by the single slide. Of course, there are so many notations and things here, but it's sort of easy to understand if you have already gone over my previous videos on deep XML, STAC, GalaXC, and Eclair, on decaf and Eclair. Okay. So GalaXC thinks about extreme classification as a link prediction problem on the bipartite graph of data points of documents versus labels, right? So essentially, given any problem like query to bid phrase classification or Wikipedia title to Wikipedia category classification, these are all extreme classification problems. So given this problem, you have the document titles as well as or document labeled text, document text as well as labeled text, right? So both of them are pretty homogeneous in nature. And therefore, GalaXC thinks of them as nodes on a bipartite graph, a graph between documents and labels. Okay. Now, and therefore, GalaXC thinks about extreme classification as a link prediction problem on this bipartite graph. So like all other deep extreme classification methods, GalaXC also depends on an embedding for extracted for every text, whether it is document text or label text. Okay, the way the embedding is extracted is as follows. You take bag of words representation for all tokens in a particular document or label, and then you multiply them with some embedding matrix E, right? That's the embedding matrix E. And then you essentially take a ReLU on top of that, and that gives you your embedded text, right? Now, unlike other methods like STAC and and decaf and Eclair, GalaXC does not really learn these embeddings. It basically just uses standard STAC embeddings or CDSSM embeddings and does not learn them at all. So module 1 in GalaXC is therefore super simple. Its job is not to learn the embeddings at all. Okay. So anyway, so we have the embedded text, whether it is the labeled text or it is the document text, either of the two, right? So basically for each of the nodes in the graph, in the bipartite graph, you have basically learned labeled, you have basically learned the embeddings, right? So essentially the pink ones or the purple ones that you see here are the labels, and then the orange ones, orangish brown ones that you see are the documents. Okay. Okay, so what next? So essentially, on top of these embeddings, GalaXC learns a graph neural network. Okay, so essentially, graph neural network, as you know, essentially is built on top of a graph. So this graph is a bipartite graph of labels and documents, and GalaXC learns a GNN. This GNN is basically a GCN, graph convolution neural network, and it involves multiple layers of convolution and transformation. Unlike Eclair, which basically says that it just involves one graph convolution and one graph transformation block, GalaXC actually uses 3 such blocks that you see here. So essentially, the first block, second block, and third block. Now, in each of the block, what happens is basically explained in this figure. So graph convolution happens like that, and graph transformation happens like that. Okay. So now that you have these initial embeddings extracted, you would take those embeddings and essentially, think of your initial A's as your X's. OK, it's the same thing. It's multiple notations used for the same thing. But A's are your X's. They're basically the embeddings of every node. And just like in a graph convolution neural network, you're going to enhance these embeddings by borrowing information from your neighbors. So this is the original embedding for the node, and these are the embeddings for the neighbors. You borrow the information from your neighbors, add it all up, and then essentially, you take this added information from the neighbors and the original information from the node. The node is n here, right? In the kth block. So remember the 3 blocks, k equal to 1, k equal to 2, and k equal to 3. So in the kth block, you're basically going to compute the representation for this nth node by just doing this kind of convolution. Okay. Now, after the convolution is done, you want to revise or transform this embedding further, graph embedding further. And the way you do this is using this transformation block. So in this transformation block, what happens is as follows. You essentially have your initial representation A. You perform ReLU on top of it. You perform ReLU on top of it. You perform do a RK transformation. Again, RK is a matrix which is learned over over training, right? And then you essentially do batch normalization, again ReLU on top, and that basically gives you delta, and this delta is added with A so as to give you the overall transform representation. Okay. So essentially, as you see, using this residual connection, you're basically adding and basically doing the residual activity, right? So that's that. So essentially, GalaXC consists basically of a very simple GNN architecture of 3 layers, right? Embeddings, initial embeddings are fixed; they are not trained over backpropagation. There is no meta label. There is no clustering. Even shortlisting I will show is super simple. So shortlisting is not based on clusters at all, right? So essentially, you just do 3 levels of GNNs, and that gives you your representations. Now, what do you do with these 3 different levels of representations, right? So this is also shown in this chart here. So given a particular label or document text, you essentially pass through the GNN architecture. You get these 3 representations. We call them as x1, x2, x3 hats. Okay. So they are actually referred as V's here, but those V's basically, it's just the same notation. The paper just used the hodgepodge of multiple notations, but actually it's the same notation. These V's basically are X's here, right? So then you basically want to do an attention-based addition of all of these so as to essentially come up with a single representation for the label or the documents. Okay. So to basically come up with these attention weights, they essentially learn these variables called as ELKs. So remember, ELK essentially is an element in a matrix, which is a number of label set multiplied by 3, because our K goes from 1 to 3. Okay. So essentially it just has 3 columns, and the number of rows are number of labels. So you randomly initialize this matrix and learn over iterations, of course, right? So that basically, so you normalize that, you get alphas, which are attention weights, which is what you use is to get your final embedding matrix. Final embedding, right? So this could be an embedding for a label, this could be an embedding for a document, either, right? So if it is basically a document, embedding for a label, you essentially also use this to learn your classifiers WL, so that these, so basically the hope is that the similarity score of the right classifier of the right label should be higher, while the classifier score for the non-relevant labels should be lower. That's what you use for training the model. Okay. So that's that. So we will also see how these X's that have been obtained here can also be, combined in a very similar way. So we will not have any alphas here, but you can combine in a very similar way to learn a shortlister also. Okay. So what is a deep XML pipeline for GalaXC? Deep XML pipeline for GalaXC is super simple and much simpler compared to Eclair. So it basically consists of only one training run. So unlike other deep XML algorithms where you have like 4 different parts, you also have 4 different parts here, but you do only one training run with the first few epochs of the training run executing module 1 and the rest of the epochs executing module 4. That's it. Module 2 and 3 are essentially just used for shortlisting and initialization and so on. Okay. So no embedding fine tuning is done. So embedding matrix E is sort of borrowed from STEC and fixed. Okay. So the way module 1 works is basically it trains the GNN parameters. Of course, you have to train, and there is no surrogate task. You basically just do the overall XC task. So you train the GNN parameters epsilon K. So where was epsilon K used? This is where the epsilon K was used for combining the information from the neighbors versus its own information, right? RKs. So what is RK? RK is basically used in the transformation block there, right? Jointly with ELKs and classifiers WL. So you train all of them together. The way training is done, of course, it will be very slow if it is done in a trivial manner. So therefore, the way training is done is by sampling in every batch. So essentially in every batch, you have some data points, and for those data points, you do the training using the positive data points for positive labels for sure. But when you consider negative labels, the way negative labels are considered is as follows. So for every batch, you first sample a random set of R labels. Okay, so this is basically just randomly sampled R labels. So the negative points are basically all those points that are all those labels which are negative for this data instance and come from R, from the set R, or they essentially are negative for this particular data point I, but positive for another data point J, which belongs to the same batch. So in some ways, they are just in batch negatives, right? So that's that in batch samples. So that's that. Now module 2, the way module 2 works, it basically uses a shortlister. So a shortlisting is basically done by creating an approximate nearest neighbor search index on label embeddings. So remember we got these label embeddings from this shortlisting. So the label embeddings can be obtained from this shortlisting stuff by taking in fact, for the shortlister stuff, you don't even use alphas. So you basically just take across ZL1, ZL2, ZL3, just take the average, and that's basically your label embedding. You put them into an ANS index, and essentially when you get a document I, you get matching labels by just searching on this ANS index. Remember, the documents and labels are both embedded in the same space because they're all a part of the same graph and so on. So therefore, you can directly just look up for labels by doing, for matching labels by querying using the document I's embedding. Okay. Now, of course, you remove those positive labels, and that forms your negative label set, which can be used for module 2 for shortlisting. Okay. Now, this shortlist is basically what is going to be used in module 4, right? So this shortlist S is basically going to be used in module 4. So the way module 3 and 4 work is as follows. You freeze GNN parameters. So module 4 does not care about GNN parameters. GNN parameters are just frozen. Okay. So your epsilon K, RK, all of them are going to be frozen. So the only thing that differs so this is one difference in module 4, that those parameters are frozen. The other difference in module 4 versus module 1 is that the negative sampling is done in a hard negative sampling manner, in the sense that you use the shortlister rather than just doing in-batch random negatives. Okay. Rather than randomly picking up some labels. So this time when you want to get negative labels, you still do these in-batch negatives. So in the sense that you take those labels which are negative for ith data point, but positive for jth data point, where j is an in-batch example, right? The other way you basically get these negatives is by basically looking at those labels which are negatives for other examples in the same batch, which are negative for other examples in the same batch. The other thing is also that these labels should actually be also sampled from SJ. So essentially, these labels should belong to the shortlister. So basically saying they are labels which are very, very close to this to this data point I, these labels are very close to the data point I, essentially you see and essentially they are labels associated with at least some example in this batch, but they are negative for the data point I. Okay. So that's that. So basically saying shortlister does not use trees, clustering trees. It's actually a much more simpler algorithm compared to Eclair. Okay. So how predictions done in GalaXC? Well, now GalaXC depends on GNNs. So when a test document comes in, it's typically not a part of your document label graph, because that document is a new document for which you want to come up with the prediction, right? Get more labels. Okay. Now, new documents therefore need to be first introduced into the graph. So you have to basically connect these new documents to some nodes in the graph. Now, you of course want to connect them to labels because it's a bipartite graph after all. So the way you connect these documents to labels is basically using an ANS index. So you basically create another ANS index. Remember, this ANS index is actually different from the shortlister ANS index. Okay. So you create another ANS index using the initial embeddings of all training labels and documents. Okay. So note that shortlister ANS index is not created using initial embeddings. It's actually created using embeddings obtained from the layers 1, 2, 3 of the GNN. Okay. So this particular ANS index is actually created using initial embeddings of all training labels and documents. Then when you basically when you essentially bring in a new document node, you actually connect the document to 4 nearest neighbors. Interestingly, these nearest neighbors may not all be labels only. They can be other documents also, as well as labels also. And once you've connected them, you just use the typical GNN architecture to essentially borrow information from the neighbors, do 3 levels of processing, get a final, get a final embedding, and make the prediction using Ws. Okay. So the shortlister essentially, basically, even at prediction time, the shortlister basically just uses the ANS index on label embeddings. So just like you had a shortlister here, which was essentially doing ANS index on label embeddings, you use the same ANS index so as to essentially shortlist nearest top 500 neighbors from this ANS index for a data point. And then you re-rank using the classifiers. So basically, once you get these neighbors, of course, you have your classifiers Ws, which is these Ws which have been obtained, which have been obtained while training. So you use those Ws so as to essentially rank the labels and get the final predictions. Okay. So no clusters and super simple, no updates to embeddings at all. So super simple architecture. Okay. So how does GalaXC perform? Well, GalaXC performs, they do experiments over several data sets. I've just shown for one of the data sets across several metrics. So, precision at 1, NDCG at 3.5, PSP at 1, 2, 3, 4, 5, and so on. They also compute PSN, PSNDCG, that is, right? And they also report other kinds of things like memory utilization or training time and prediction time and so on. So what do we observe from here? First observation is that unlike many other architectures, GalaXC is not an ensemble. It just is a single model that helps to have the model small in size, as well as it helps in maintenance in production systems. GalaXC can be up to 18% more accurate, as you can see from this table. So it's basically the most accurate compared to several of these deep learning as well as non-deep learning baselines, right? While being 2 to 50x faster to train on a single GPU. So it's super fast to train, right? Performs best on the tail. So these quantile plots actually show. This is the tail bucket. This is the head bucket, right? And these are buckets over labels. So what does it show? It basically shows that on the tail buckets, GalaXC actually gives you better results on both the data sets. Okay? So it performs best on the tail. Okay. On the head, it may not be as good. It may not be as good as compared to other algorithms, but on the tail, it surely gives you really good results. So in short, the GalaXC algorithm incorporates neighborhood information with the help of a joint graph over documents and labels. There's a lot of things, labels and documents as equivalent nodes. In many cases, the label text and document text are pretty homogeneous in nature, so that helps. Right? GalaXC also incorporates per label attention mechanism that attends to multi-resolution embeddings at different layers from the GNN, obtained using a GNN architecture. It can be up to 18% more accurate and 2 to 50x faster compared to other state-of-the-art XC algorithms when trained on a single GPU. Okay, here's the code for you to try out. So that's it for this video. Thank you for watching. Hope you liked the video. Connect with me on my LinkedIn or look at my research on my homepage.